Hey guys, welcome to your Chapter 6, Lesson 4 notes on applications of linear systems. Finally, though, when are we going to use this in real life? Lesson. By the end of the day, you'll be able to choose the best method for solving a system of linear equations. In order to choose the best method, you must first remember what the methods all are. So let's take a quick review session. In our first lesson of the chapter, we learned how to find solutions by graphing. When the two lines intersect, the point that they intersected was their solution. There was one solution here. If we graphed two lines over here and got that they were the same line, that had infinitely many solutions. An infinite number of solutions. And finally, when we graphed two lines and turns out, oh shooties magooties, these guys are parallel, there is no solution to this system of equations because there is no point that lies on both lines. Then we looked at substitution. In substitution, we solved for one of the variables, and then we replaced that value in the second equation. So we took that 2x minus 1, we plugged it in for y to get 3x minus 4 times 2x minus 1 equals 2. And then, of course, you solve for x and then plug it back in to find out what y is. Once you figure out what x is, plug it in here, and that tells you your y. After that, we decided that we wanted to eliminate some variables. When you eliminate variables, you need to add equations together, making sure that two of your terms will cancel out. Sometimes they don't come this easily, and you need to multiply, do some fancy multiplication to one or both of the equations. Anyway, so now you line them up, you add them up, so we'd get 9x equals 14, solve for x from there, and then plug x back into your equation to figure out what y is. So those are the three methods. Here's also a cheat sheet of when to use your methods. Graphing is super easy. If you have a graphing calculator, it's really helpful if you need to see what's going on. If you want a visual display of the equations. It's also helpful if you just need an estimate. If you don't need an exact answer, you can just kind of look at the graph and go, oh, when x is like 4. Okay, so if you just need to estimate, you need to get close, graphing is good. For the other two, if you need an exact answer, you can use either substitution or elimination. If you have an equation that's already solved for a variable, then definitely use substitution. It's going to be so easy. Alternatively, if it's really easy to get it to be solved for one of the variables, then go do that. If it's not easy, elimination is going to be your best bet. If you happen to find opposites in your equations, just like we had a plus 3, minus 3 up here, that's nice. Or basically, if the other guys don't work out, then just go with elimination. Okay, cool. So all day today, we're going to use any one of these strategies, any one of these methods. You can honestly just use which one works best for you. So let's start by finding a break-even point. A little bit of background. Break-even, when you're talking about sales, when you break even, that's when you hit 0. That's when the cost of doing something equals the profit. For example, if it costs $35 to get supplies for Candy Grams, and you charge them $1 a piece, then when you sell 35 Candy Grams, then you break even because you spent $35 and you earned $35, so overall you break even. Okay, so in this case, we're not selling Candy Grams, instead we are making hats. The material for each hat costs $5.50, and the hats sell for, so I'm gonna immediately say material costs $550 because that'll put us in the whole $5.50. The hats sell for $12.50 each, so that's profit, so I'm going to make that green. The designer spends, here's another deficit, $1,400 on advertising. How many hats must the designer sell to break even? So the question that we're going to want to answer is how many hats? Therefore, our first variable, I'm going to say x is the number of hats sold. But we also want to know break even. When does our cost going to equal profit? So I'm going to let Y represent all the dollars. Okay. So now that we have the information, let's put it into a system of equations. Our first equation, I want to represent cost. Okay. So I know that Y represents cost. So I'm going to say Y equals, and then what are my cost things? What are my costly ideas? Well, each hat costs 5.5. Remember, number of hats is X. So I'm going to say 5.5 times X. Another cost is $1,400. This is a one-time payment of $1,400 on advertising. It's not that we advertise $1,400 per hat. No, it costs 5.5 per hat. So that's a cost equation. Now let's look at our profit. Our profit equation represents how much we earn per hat. Well, the profit earned, the amount of money we earn per each hat is 12.5. So that'll be 12.5 times X. Now we have our system of equations up. Now all we need to do is solve it. So when I look at this system of equation, I notice, hey, it's solved for Y and it's solved for Y. That's screaming substitution for me. So I'm going to solve this by substitution. That means setting our Y expressions equal to each other, because you agree that Y equals Y, therefore these two must be equal to each other. Now that I have my system, my one equation up in place, again, this is a representation of Y equals Y. So in our first equation, we know that Y equals 5.5x plus 1,400. That's where this comes from. And then in our second equation, we know Y equals 12.5x. So Y is 12.5x. Y is also that guy. So now we know that they're equal to each other. We can solve for x. First, I want to get all the x's to one side, so I'm going to subtract 5.5x from both sides, giving me an even 1,400 on this side. It's funny because it's even, but also of 7x on that side. Now to continue to get x by himself, I'm going to divide both sides by 7, giving me 200 equals x. So that means that we need to check out what x is. X means the number of hats sold. So we need to sell 200 hats. How many hats? 200 hats must be sold. So you sell it to all of the underclassmen and you should be fine. Okay, great. So that's how to find a break-even point. That turned out really well. You can have 200 hats. That's a feasible real-life situation. We call that a viable situation. Viable, like vitality or la vida, means life. You can do it in real life. It lives. So a viable solution is one that makes sense, that works, one that's practical, one that you could use in real life. Okay. Sometimes you have a non-viable solution. Non-viable means it does not work. We'll get there. In order to figure out what a viable solution should be, you need to set constraints. I'm going to make them blue because we haven't used blue yet. To constrain is to limit something. It's to hold it. It's to bound it. So constraints set a limit on your values, set a limit on your variables. Say, hey, it doesn't make sense, for example, to have negative hats. That doesn't work. So let's put this into practice. Let's say that at the zoo they have leaky tanks. Yikes. One tank contains 10 gallons of water and leaks at a rate of 2 gallons per hour. Oh no. The second tank leaks. Man, why is this so hard? The second tank holds 6 gallons of water and is also leaking at 4 gallons per hour. Yikes. Okay, so to just kind of think about this real quick, we've got a big tank that's leaking slowly, and we've got a little tank that's leaking quickly. When will the tanks have the same amount of water? Okay, so that's our question. What time will the tanks have the same amount of water? Well, I don't know, but we certainly can find out. So what are we going here? We want x to represent our answers to the equation. When? So x needs to represent time. Let's say hours, because we're given hours. So time in hours. Okay. And then also y should be the gallons of water, because that is the other things that's changing. Okay, so now let's set up a system of equations by relating one tank and the second tank. So in our first tank, the amount of water is represented by its starting, which is 10, and then we lose 2 gallons per hour. In our second tank, the amount of water is represented by our starting value of 6, and we're losing 4 gallons per hour. So let's look at this guy. I also see again that we have a substitution here, because we're already solved for one variable. So let's do that. Let's set our y values equal to each other. So I'm saying that 10 minus 2x is equal to 6 minus 4x. Again, we're solving for x here. So I'm going to go ahead and I'm going to add, I switched my color scheme on you, you're welcome. I'm going to add 4x to both sides this time, because then these guys will cancel out, giving me a 6 equals 10 plus 2x. Then we'll subtract 10 from both sides, giving us negative 4 equals 2x. And finally, divide both sides by 2. So we have negative 2 equals x. Awesome. So our answer is negative 2. But that makes no sense, because remember, x represented the time. In negative 2 hours? What? That's a non-viable solution. That doesn't work. You can't go back in time 2 hours ago and then they had the same amount. Come on. This is a non-viable solution. What this means is they will never be at the same level. They will never have the same amount of water in them. Why? Because let's look at this practically. Our first tank starts out with a lot and is draining slowly. In a very crude graph right here, he starts out with a lot and is draining slowly. Our second tank starts out with only 6 and is draining faster. So they won't ever have the same. That's why x is negative, because they intersect back here. So that doesn't make sense. So never. They will never have the same amount. Alrighty. So we've talked about non-viable solutions. There's another type of problem that you can have with systems of equations. A very common real-life application is with currents. So if you ever see a problem about currents or wind resistance, or people working together, people working against each other, this is this kind of thing. So just a heads up. In the US, we have steady west to east winds. That means the winds are blowing like this. They go this way. They go west to east. That's an arrow, like that. Okay. This is important because they affect how planes travel. So when a plane travels from the west to the east, we call them tailwinds because they're at the tail of the plane. They're pushing the plane along. So the plane will actually travel faster going from LA to Charleston than if it were going east to west from Charleston all the way to LA. It will actually move more slowly. So we call that ground speed. Anyway, so tailwinds increase the plane speed relative to the ground. It moves faster. And when the plane travels east to west, there are headwinds because it's going against the wind. The wind is at its head, which decrease the plane's speed relative to the ground. So what this is looking like in like a graph, how to figure this out. When you're traveling from west to east, that means the air, your air speed, we call it your air speed. Oh, whoops, I put them in the same thing. Sorry. This goes down here. Your air speed is going to be added to the wind speed. And that will get you your ground speed. So when you have your instruments reading one thing, but then you also have the wind pushing you, so someone from the ground thinks you're going faster than you actually are. In fact, this is not to scale. It's more like that. So airspeed plus wind speed will equal your ground speed. However, when you're going from east to west, the opposite occurs. You need to take how fast it looks like you're going, but then you need to subtract. Just kidding. Your airspeed is equal to your, that's an equal sign. Your airspeed is equal to your wind speed minus your ground speed. Did I write that? I'm going to draw a picture and then I'm going to say it to you again. Because the wind is always blowing this way. This is wind speed, and then ground speed is, yeah, that's what it looks like. Haha! So your airspeed is equal to the wind speed minus the ground speed. No, I lied. It's I had it first the right time. I had it right the first time. You know, it's a good thing I'm not a language teacher. That would have been embarrassing. Okay, here we go. So, yeah. Oh, look, I drew a nice picture for you. So this is what's happening. When you go from west to east, you get pushed because the air is pushing you a little bit. So you go faster. When you're going from west to east, the wind is going against you. So you go more slowly. In fact, I'm going to take this image and move it down here because we're going to need it. Okay, so let's say you are in fact flying from Charlotte, North Carolina to Los Angeles, California. At the same time, someone else is flying from LA to Charlotte. The airspeed of each plane is the same. Nice. The ground speed is shown. What is the airspeed? What's the wind speed? Well, we need to figure out what our airspeed, wait for it, what our airspeed and what our wind speed are. What is the airspeed? It literally asks. So let's make it a variable. What is the wind speed? It literally asks. Hey, let's make that a variable too. Nailed it. Okay. Do I even need to define them? Air, wind. There you go. Okay, so we also know from above that I'll just zoom in. Our airspeed minus our wind speed is going to be our speed from Charlotte to LA, which was 495. And then our airspeed plus our wind speed is going to be our trip from LA to Charlotte, which is 550 miles an hour. Isn't that so nice? That's so nice. And that should make sense, right? If we're going against the wind, we're going slower. We're taking the wind away. But if it's pushing us, they're working together. Okay, so how are we going to solve this system? Well, I look at these guys and I say, wow, this eliminates really quickly. I got the plus W minus W. That's excellent. Let's use elimination. Entonces, wow, that happened. Let's use elimination then. Okay, so A plus A gives us a 2A, if you're Canadian now. And 495 plus 550 gives us 1045, which is not the current time. So that's also exciting. Alrighty, now to solve for A, we just need to divide by 2 on both sides. So A is 522.5 miles per hour. So that's how fast we think we're going, 522 miles an hour. But either way, the wind is working for or against us. So we know our airspeed. Let's plug this guy in to one of our equations and figure out what the other guy is going to be. I like positive numbers, so I'm going to go with our second equation. Of course, you can do the other one if you want and see if it comes out the same. So that gives us 522.5 plus W equals 550. We subtract 522 from both sides, giving us, pause for dramatic effect, that W equals 27.5 in miles per hour. So the wind is blowing at 27.5 miles an hour. There you have it. We've got our wind speed. We've got our airspeed. Yay. Cool? Cool. So are you going, let's see, where did we put our little current thing? Our current cheat sheet. Let's put a current cheat sheet right here. Are you going with the current? Then use, actually let's just put him here. You will add them together. Are you going against the current? And the current is working against you. You need to subtract it out. That goes here. Hey, there you go. Okay, notice we used elimination. We used substitution. We could use graphing. I kind of use graphing a little bit. It really doesn't matter. But whatever you do, whatever system you use, whatever method you use, I hope you have a fantastic time on your homework.